Hello, and welcome to this presentation on direct interfacing of Micro-Epsilon sensors to a UR3 robot. My name is Glenn Wedgbrow, and I am the Business Development Manager for Micro-Epsilon here in the UK. In this session, I will be discussing how we interface different sensors from Micro-Epsilon to the UR3 robot based on whether they are a 1D, 2D or even 3-dimensional measurement sensor. So let us consider for a moment the customer's perspective. They will come to us with a target or targets, and they will have measurements they want to make, and usually they will have specific requirements for communicating to their process or system. We at Micro-Epsilon will have a range of sensors and technologies that can solve that measurement task, and each sensor will either have the capability for direct connection to those systems or an interface module that can convert the standard output from the sensor into a suitable signal or protocol. Our sensors are capable of measuring changes from as small as 30 picometers up to distances over 200 meters. We can detect colour changes much finer than a human being, and we can measure temperatures from -50 degrees C up to +3000 degrees C. At Micro-Epsilon, our goal is to provide you the right sensor technology and output that solves your task. Robot use is ever increasing in industry, and more we see customers who are looking to integrate Micro-Epsilon sensors onto their robots. In some cases they want direct communication, in others they use intermediate PLCs for control. In order to be able to better understand and support that integration, we've invested in a UR3 robot. Initially this was just for our own use to simplify sensor positioning on targets, but also to understand the requirements for integration of our sensors. The UR3 Cobot has a number of connection possibilities, including analog and digital I/O, that can be used for triggering sensors or receiving measured values from displacement sensors. An alternative in the modern world is that of industrial field bus networks such as Profinet and Ethernet IP. But here you have to take caution, as the robot is considered a client rather than a server. Only if you're using MODBUS are you able to use the robot as the server and thus control devices on the network. In its most simple form, the robot can control a process by sending a trigger signal to a sensor to take a measurement. In this first application, the robot is programmed for 8 positions, and using the mounted surfaceCONTROL 3D, the UR3 triggers the sensor to start a 3D measurement at each position. The final 2 positions in the sequence just show how the surfaceCONTROL is able to still make a measurement even if the target is presented tilted. The pass and fail decision can also be passed to the robot for further decision making if required. Next we look at the analog input. In this video we use one of our popular laser triangulation sensors, the ILD1900, to measure the distance to a target. Laser triangulation sensors have a measurement range that starts from a defined standoff. At the start of the range you get a 4 mA or 0 volt output, and at the end of the range you get a 20 mA or 10 volt output. This distance is transferred into the robot controller and can be used to accurately position the robot above a target or correct its position, say for focusing a laser marker or weld torch. Most importantly, you should scale the input on the robot controller to ensure the correct readings based on the sensor's measuring range. Please note the UR3 Cobot program uses standard units such as meters, amps and volts, so in order to get millimeters, milliamps, millivolts, you may need to divide or multiply the values you receive by 1000. When we move from one-dimensional measurement to 2 dimensions, it becomes more interesting in that you now have at least 2 pieces of information you can send to the robot. In this case, it makes more sense to transfer data digitally rather than by analog. Our scanCONTROL sensor is a laser line profile sensor that projects a laser line onto the target. The CMOS camera inside the sensor converts the received information into black and white, and then the sensor processes this image to provide calibrated XZ coordinates of points across the line. This point information can be processed inside the sensor for measurements to be made and transferred to a PC or PLC in a range of interfaces. In the case of the UR3, we are looking at the MODBUS interface. scanCONTROL is offered in two versions depending on whether you are processing the raw profile data yourself or whether you want the sensor to process the profile for you. We refer to this as a smart sensor. For adjusting the scanCONTROL device, we use scanCONTROL configuration tools to select and configure the measurement programs and the sensor settings. When using the smart sensor, you are able to make a range of inspections and measurements from the profile line data, including width, height, finding extreme points, steps, angles, and circular information. Plus, you are able to combine results together to create further useful values. In order to use MODBUS, you must first configure the sensor to deliver measurement values via the MODBUS. This requires you to activate the MODBUS protocol on scanCONTROL, and then after setting the measurement program, you can select the values from the program to be assigned to the MODBUS registers. The scanCONTROL sensor transmits measuring values as 16-bit integer or 32-bit integer. Configuration tools shows the number of registers that are used for each measuring value. If 2 registers are needed for one value, you need to add the second register in this dialog. The corresponding registers must be set in the UR3 controller so it knows what to receive. According to the sensor type, the integer values have to be converted to be shown in the original format. Once scanCONTROL is integrated to the robot, it can be taught to follow a target. Here the robot program is defined so that the reported maximum point position needs to be 0 mm, i.e. central in the X-plane, and 290 mm in the Z-plane. The robot uses the information provided by the sensor to adjust its position to maintain the given criteria. Once configured, scanCONTROL sensors are also able to work without the PC and can still deliver the measurements to the robot to allow the continued positional control. The self-contained sensor head is perfect for integration onto any robot. We have already seen surfaceCONTROL 3D being used with the Cobot in a simple trigger function for inspection of a target. But more and more 3D sensors are being used to find targets and reposition the robot accordingly. The challenge here is that the coordinates transferred are in float format, which the robot controller cannot directly handle and must be converted before use. The handling of the main 3D data is performed on a PC, like our industrial processing unit, where the data from the surfaceCONTROL 3D is received and processed using our intuitive 3D Inspect software. After parameterization in the software, the coordinate or measurement data is transferred to the robot via MODBUS as a float value. "3D Inspect" outputs coordinates in the format of 32-bit float values across 2 MODBUS registers. The UR3 interprets the 3D Inspect signal also across 2 16-bit registers, MODBUS Signal 1 and MODBUS Signal 2. In order to convert the integer value to binary, we use a function built into the UR software called integer to binary list, which is highlighted blue. This creates a string of 32 or true or false conditions, which is assigned to a variable, and each variable is then passed through a sequence of if-then statements to convert it into zeros and ones. So register 1 has been converted from 16-bit to 32-bit, and this is repeated for the second Modbus signal. Once all 16-bit variables from the two Modbus signals have been converted into zeros and ones, the list is reconstructed into the required 32-bit binary string. The 32-bit binary list is then converted using the UR function binary to float, highlighted again in blue. The function converts the binary based on the IEEE 754 standard for floating point conversion, so that we end up with the correct positional value for the robot. So, to illustrate the process, we have a surfaceCONTROL 3D mounted on the UR3 and have programmed the surfaceCONTROL to detect the position in X, Y and Z of the highest point, and then reposition that to the centre of the surfaceCONTROL's measuring field. Each time the target is adjusted, the surfaceCONTROL is triggered to find the target. surfaceCONTROL then reports the new coordinates to the robot, which in turn repositions itself. These are the sort of functions that will be useful for pick-and-place applications. Robots open up many possibilities for automation in a customer's process, and sensors can be used to inform the robot about the target presented in front of them. The use of 1D, 2D and 3D sensors integrated on the robot can improve reliability, increase speed and ensure the process is running smoothly. Although I've shown some integration options with the UR3, we are able to work with any robot supplier, as these videos highlight. So, in summary, we have seen how 1D, 2D and 3D sensors can be configured and integrated directly into a UR3 robot. The choice of sensor and interface is purely determined by the application and robot used. An intermediate PC or PLC may be preferred for more complex tasks. You can find out more information about our products on our website, plus video content on YouTube, and of course via LinkedIn. Please make sure you like, follow and subscribe. Thank you.